So I thank you guys all for coming out. I really appreciate you all being here for the Sustainable Gathering event. Once again, in supporting the Sustainable Dream Festival, which is a multi-day music and art event that has music, art, and environmental organizations, nonprofit organizations, and activists. And it's going to host a whole lineup of music and arts, but also a whole lineup of presentations like a TED Talk about environmentalism. And so I want to give you guys a hint of what that event is going to be like. And so that's when we started this event, which is the Sustainable Gatherings, which happens every other week right here in Alexandria at Galactic Panther. And so one thing to keep in mind when you're talking about science and science education, I myself am a science educator. I teach physics and calculus and chemistry. And one thing that I always keep in mind when I'm teaching is using history as correlated with the science and considering how these scientists came across with these conclusions and found this knowledge about the world around us. So for example, when I teach about Pythagorean theorem, I talk about Pythagoras and how he used geometry when he was building and constructing. And when I teach people about calculus, I tell them about Isaac Newton, who used calculus to predict accelerating objects and to investigate gravity. And so I think it's important to see the uses and the history of how this knowledge came about when you're teaching and when you're learning something new, so that you can understand what motivations people had to investigate those topics and what uses it has. And I find that that helps me a lot when I'm teaching calculus students to see how it can be applied to physics, and when I am teaching geometry students to how it can be applied to so many things like construction and building and engineering. And that always gauges interest, and it really grounds the information that comes with the science and allows you to really understand how it all comes together. And so one more complex subject that people are talking about currently in the world is climate sciences. And I think when we discuss climate sciences and environmentalism, it's important to understand that this isn't something that, is just written on a rock that we found. Just like calculus and Pythagorean theorem, right? It was discovered through a lot of investigation and research and math, rather than just being told to us by some external force. And so because a lot of times when people are learning in school, they feel like this information is just told to them, and they don't feel like they personally learned it. So I think that's why it's important to incorporate the history of how this knowledge came about, so that people understand how it came about and that they personally engaged in this investigation. And so that's why I invited the NOAA atmospheric scientist Mark Iredell to come out and speak about the history of climate sciences throughout the centuries and how we came about to these conclusions and this information that we know about climate sciences. So without further ado, I'd like to bring up Mark Iredell to discuss climate sciences.
Thank you. Thank you, Jono. I'm going to be tripping on any wires here. Thank you. So, here's my title. You've already seen it up here. Oops. No, it's here. Okay. So I got my PhD at the University of Washington in 1988. I've since then worked at NOAA, National Weather Service, developing weather prediction models, in particular the GFS, or American model as sometimes called. And now I'm retired, and you can see I'm in retirement outfit. And I'm also a founding member of the recently established Virginia chapter of Elders Climate Action, and I put the way how to get there for eldersclimateaction.org, Virginia chapter, if you're interested. So, looking from space, ask, what are the balancing energy fluxes on Earth? This is what was a question 200 years ago. They're trying to figure out why is the energy balance on Earth balanced, and what are the different fluxes? And so, and here's a picture of how Joseph Fourier, back in 1824, looked at it. There's the sun that he knew, and then there's the infrared radiation to space from Earth. So the sun warms the Earth, the infrared radiation leaves Earth, cooling Earth, and it should be in balance. Okay? Please interrupt if any questions are coming up, because I'm just going to go blazing through. And that's Joseph Fourier, and what he calculated was, knowing the sun's radiance, Earth should have an apparent mean temperature of just minus 18 degrees Celsius, or 0 degrees Fahrenheit, because he knew how much temperature at 0 degrees the Earth would radiate out to space, and that would equal the sun's irradiation, which he also knew. But, of course, the actual mean temperature in his time was 57 degrees Fahrenheit, and today it's 59 degrees Fahrenheit, because we have warmed it up a bit. And so there's this big imbalance. And so Fourier, thought, well, maybe he's missing an energy flux, but if not, what moderates the temperature is, he felt, was that the Earth is warmer because of its atmosphere. The atmosphere is transparent to visible light, but it absorbs and emits infrared light, some of which goes to space, but some of which comes back. And so, effectively, the radiation from Earth comes from a colder upper level of the atmosphere, and that's how it's in balance, even though the surface is still warm. And he even surmised that human activities could affect climate, but he thought the climate change like that would take centuries. He said, the established and progress of human societies, the action of natural forces can notably change, and in vast regions, in the course of many centuries, the average degree of heat. Of course, he said that in French. He was from France, but this is a translation. And there he is again. Okay, so then we move on to the mid-19th century. What components of the Earth's atmosphere behave like a greenhouse? And you know the answer to that, right? They're the greenhouse gases. So Foote in 1856 and Tyndall in 1859, Foote from US, Tyndall, he was Irish, experimentally showed that both CO2 and H2O are greenhouse gases. And we know today it's because they actually have 3 atoms and they have certain vibrational modes that create this infrared energy. So they both absorb and emit infrared radiation. And Foote actually said in 1856, an atmosphere of that gas would give to our Earth a high temperature, and if some suppose one period of its history the air had mixed with a larger proportion than present, an increased temperature must have necessarily resulted. So they were already talking about climate change with respect to greenhouse gases back then. And here's a picture of Foote in her laboratory in America. So she's a woman. And so why did Tyndall originally get credit, given that Foote published first? When I took atmospheric science, I never heard of Foote, just Tyndall was in all the textbooks. And the reason why, perhaps because she was a woman, but it's also because she was an American amateur scientist, publishing in the major American journal, the American Journal of Science, but which was pretty obscure in Europe. And America was a backwater in science in the 1850s, believe it or not. And it was only later that Lincoln established the National Academy and science became more of a profession in America. And it is not until 2011, when Foote's journal article was rediscovered, and her contribution became well known. And I don't think Tyndall read it, and he actually did a little bit more exploratory in his experiments, so they both get credit. So, and oh, yes, I forgot, there's a follow-up question. Eunice Newton-Foote seemed to be a forward-thinking American woman. Could she maybe have attended the Women's Rights Convention in Seneca Falls around the same time? Yes, she did. There's her name down here, right underneath Elizabeth Cady Stanton in the honor signatories of the convention for women's rights. Okay, moving on. Now in the late 19th century, how much temperature difference would doubling CO2 concentration make? This is our question. One of the reasons they wanted to look at it was not thinking about global warming, but also thinking about what are the causes of the ice ages that recently had much better evidence from, and they wanted to know what mechanism caused the ice ages. And they thought greenhouse gases is a good candidate. And of course they were right. And Arrhenius and Hobboom, I think you pronounce it that way, first calculated in 1896, doubling CO2 and whatever changes in H2O would come from that would give a warming of 4 to 6 degrees Celsius. And that's pretty close to what we think today, because it's around 3 degrees Celsius is the latest IPCC, is the sensitivity of doubling CO2. And they surmised that doubling might take 30,000 years, given how much coal burning was going on in 1896. So they did not consider how much more we do in the 20th century. And the side fact is that Arrhenius did all the calculation here in his study, and it took like a year, with pencil and paper, no computers, of course, back then, to do this calculation of different levels in the atmosphere and all. And the theory is he may have been, it was distracting him from his marriage, which was falling apart at the time, so he just went off to be alone in his study. Huh? All right, that might be just a rumor. There were this made the newspapers, at least the Rodney and Automata Times, which is somewhere near Wellington, New Zealand, said, coal consumption affecting climate. The furnaces of the world are now burning about 2 billion tons of coal a year, and when this is burned, uniting with oxygen, it adds about 7 billion tons of carbon dioxide to the atmosphere yearly. This tends to make the air more effective blanket for the Earth and to raise its temperature. The effect may be considerable in a few centuries. So they were wrong about a few centuries, but that rest of the article is very good. I'm really amazed. Some other newspaper articles went a little overboard, like this one from the Selma Morning Times, Selma, Alabama. It said, hint to coal consumers, Swedish professor Sven Arrhenius has evolved a new theory of the extinction of the human race. He holds that the combustion of coal by civilized man is gradually warming the atmosphere, so that in the course of a few cycles of 10,000 years, the Earth will be baked in a temperature close to the boiling point. He bases his theory on the accumulation of carbonic acid, which is what they called CO2 back then, in the atmosphere, in which acts as a glass in the concentrating and refracting of the heat of the sun. So they got a few things wrong, but and there is Arrhenius in a happier moment. You can tell he's happy because he's on his second marriage by now.
He doesn't look happy.
He's Swedish, that's how they look at him. And so after Arrhenius, we got serious about anthropogenic global warming in the 20th century, right? Okay, that was a rhetorical question. So, because from 2 billion tons of carbon back then, which is 7 billion tons of CO2, like that New Zealand article said, per year, emitted in 1900, now we are doing 40 billion tons of carbon, 130 billion tons of CO2 per year. We have jumped the Sharknado. But if we just consider what this talk is about is the science, not our social response, we just consider what climate science. Actually, climate science really did get going in the 20th century because there was skepticism, even though Arrhenius won the Nobel Prize for completely different work in chemistry. There's skepticism about his year-long calculations, and it drove a lot of research. But before we get to that, I can ask a couple more outstanding questions that people sometimes ask about climate science. So CO2 and H2O are both greenhouse gases. Why are we worrying about just CO2? Anybody? All right.
Water rains down, right?
Good. Water rains down, and that's exactly right.
Oh,
Because there is a lot more H2O in the atmosphere than CO2, but the amount of H2O is totally dependent on the temperature of the air. If the air is cold, H2O condenses out and rains, as you say. If the air is warm, H2O evaporates into it most of the time. So there are exceptions, but this is a general rule. And so we don't have control over the H2O, temperature does. And so the CO2 concentration, plus we should mention other greenhouse gases like methane, affects the temperature, and the temperature affects the H2O concentration. In other words, CO2 is the control knob, and H2O is the accelerant. Okay, more questions. Should we worry about the CO2 we exhale? No. The CO2 you exhale never really left the carbon cycle, because it goes from atmosphere to photosynthesizer to oxidizer back to atmosphere, and that carbon came from the apple you ate from the tree that recently took it from the atmosphere. That's what it goes by. There he goes. So even if you didn't eat the apple, so the carbon from the apple you ate from the tree recently came from the atmosphere, and even if you didn't eat it, it would drop to the ground and get eaten by other oxidizers like mold or bacteria. And then some carbon might get buried, but that comes on a different time scale. And one more question. We observed that carbon has increased the atmosphere over the past century. How do we deduce that the excess carbon came from buried fossils? It's not conclusive, but the very strong evidence that because we see that the isotope signature of the excess carbon is the same as the signature of buried fossils. Okay, I might skip through some of this next page, showing the other scientific progress we've made up until more recent days, and I'll put it up there for thing. And then finally in 1967, we first started doing computer modeling of the changing climate. Should I go further, or should I go through this page? Okay.
So they're starting to realize that carbon was increasing, I see, in 1960.
Yes, Keeling first started, well, they already realized climate was increasing.
Yeah, measuring it. Yeah.
And then he started really measuring it like daily in 1960. He started measuring, they have a famous station on Mauna Loa that's been measuring carbon dioxide since 1960. Mauna Loa is in Hawaii. The air from it comes nowhere from any industrial area because it's out in the middle of the Pacific, and so that's a very pure measurement. And you can see it's called the Keeling curve now. It gradually increasing up to today, and it really hasn't turned around. Even if you look at 2020, when our emissions went down a little because of the pandemic, and everybody was home and some industries shut down, but because of the momentum of the carbon even the emissions went down, the carbon was still going up just from past emissions. And so really you can't even see the pandemic in this Keeling curve. And so the modern age, now that we're in the computers, and then we have some alphabet soup because all kinds of organizations are involved. So there was a global consensus from the science end point of it, from the 70s to the present, and Charney in 1979 issued the NRC report, which is a group of international scientists at the time, found that the ECS, or equilibrium climate sensitivity, the same number that Arrhenius computed way back when, was 3 degrees with an uncertainty 1.5 degrees. I'm going to say the modeling I did is the National Weather Prediction and climate modeling are very similar, but the usage is different because they have similar resolutions in physics, but NWP models, numerical weather prediction models, run daily from observational data simulation, give us a 1 and 2 week forecast. The climate models run longer and repeatedly to determine the response from forcings, such as human carbon emissions. And then the IPCC, Intergovernmental Panel on Climate Change, was established in 1988 by the WMO, and they've been issuing reports ever since then. There's a picture of Joel Charney, who I mentioned in the first line. He was the PhD advisor of my PhD advisor, and I met him once in the 70s. So what has the IPCC done? There's been 56 international sessions. They've been finding these sessions involve pretty excruciating they call it least common denominator work, and that they have to get consensus from everybody, no matter what their interests are. But nevertheless, it's accepted work is very important to the world. And it's 6 massive assessment reports. And here those are. The latest one, the 6th, is just coming out, starting last year. They're still not issued the synthesis report later. That should be later this year. But but so far, the conclusion is the physical science basis one came out in August 2021, and that's more or less the topic of this talk. My last 2 slides that I'm going to show is that I took from that report is the key conclusion of this report that I consider. And then just last month, there was the impacts and adaptation and vulnerability report, basically all the downstream effects of global warming, coastline loss, crop loss, flood control that STAR works on. And so, and then these, I should note, by the way, that neither of the reports really deal with another very current problem we see with fossil fuels, is that they produce war and terrorism, like the fossil fuel producing countries such as Russia and Saudi Arabia. And I think that's very clear today. So, what did the IPCC report say last August? They looked at 5 different scenarios of, these are our choice of how much emissions we'll be doing. This is what we have control over. Our CO2 emissions from 2015 to 2100. And they looked at 5 different scenarios. The very low, you can see we cut down to half just in the next few years. So that's very drastic. You cut down in half by 2030. The next lower ones they call low. It's a gradual cut down, but it is a cut down. The intermediate keeps the same until maybe after 2050 we start lowering our emissions. And then the other 2 increase emissions all the way. And then they take these emission pathways, stick them in the models, and they have lots of models to work with, and they can take a consensus of the models, run the physics, and see what temperature changes there are. And they also looked at other things, also like sea ice, but this is what I'm going to be showing, the temperature. And you can see the very low emissions keep us at below, right around 1.5 degrees Celsius. The low emissions at least keep us below 2 Celsius. The other ones push us above 2 Celsius, which should create havoc. And especially the high and very high. I mean, we would really have a horrible time living in 2100 with a 4 degree Celsius increase. And so, sorry, that's all I have, but I will take questions. Thanks.
Does anyone have any questions?
I'm glad you guys are here.
Questions?
I'm glad you're here.
What model do you think is gonna play out?
Of those
Oh. These?
yeah, with high,
All right, let's go back to what we have control over, which is that. So these are the 5 emission pathways we have control over. Blue is we cut in half by 2030. I don't think that's going to happen. The politics isn't there. People don't want to stop doing fossil fuels. I think there is some hope for the, I don't know, is the real answer, but there is some hope. Yeah, there is some hope that we can gradually cut down on this low one, or at least not emit any more than we're doing now for the yellow one. So those are the 2 ones I'm grasping on.
Thank
yeah, it would be hopeful to stay between probably the yellow and orange.
Well, I want to be below the yellow or below.
We want to be.
Yeah. So, anyway.
So why don't you go to the next one? I'm just curious
Yeah.
after having that conversation.
So the low keeps us below 2C. The intermediate keeps us, it would be 2.5 degrees C.
you.
Almost 3.
Yes, okay. It'll be bad.
What happens when we hit 2? I mean, what's the Earth gonna look like?
So,
What's the sea level rise look like?
yeah, so that's the part that I did not study up on for this talk, sorry. And so, but it seems like the real bad impacts, most of the bad impacts that everybody's afraid of, start happening already at 2 degrees C. So if we go to hit 2 degrees C, we'll see some of those bad impacts. Above 2 degrees C, will get worse. Already we're going to have some issues with sea level rise. I think Miami is in big trouble. Venice is in big trouble. So we probably just lose those 2 cities. And then we'll have to move.
What about Netherlands?
Yeah,
New Orleans?
Netherlands.
Some islands.
And New Orleans. All the islands.
New Orleans is already gone, isn't
Well, yeah, I mean, New Orleans will be, New Orleans is inland, but it's below the
it? Yeah, it's already
river
below sea
level.
level.
Yeah, below sea level. And it had the dikes and it's actually below the Mississippi River level.
Yeah,
So,
absolutely.
I mean, it's just at a high risk.
They just don't know it
And the Netherlands, already we know they have a lot of land below
yet.
sea
Yeah,
level.
well, they're
So
building
they're
a lot
also-
of sort of underground tunnels
For water?
for water.
Yeah. Yeah, it only gets you so far.
Yeah, right.
Well, even New York is starting to plan for.
Right. So parts of New York, Central Park, New York is actually pretty high, so people could all move there, but a lot of New York is not.
They have
And so-
about 3 concerts.
Yeah.
The subways will flood and like they
Yeah,
already
that's right.
started.
Yeah.
Urban flooding, we don't talk about enough.
Yeah.
What?
Yeah.
Urban flooding?
Yeah,
Yeah.
Oh,
absolutely.
yeah, that's a pretty
Yeah.
problem.
There's so much
And,
urban stuff under.
well, Miami is already getting urban flooding. They get what they call good weather flooding. It hasn't rained anywhere,
They're
and
pumping
suddenly they get
water
sort of
out
flooding.
already,
Yeah,
and they're still building, it's crazy.
yeah.
But also, I mean, our food production,
Right,
based on climate, wheat and other things.
yeah.
Um,
So that's a very complicated question because, we depend on a variety of foods, and so one will be, will lose, but another might gain. But I think it's really hard to support our world population if it
Well,
gets too
tell
warm.
them about the Kernza flour grown in Minnesota, or wherever it is, the bread out there.
Yeah. So, this morning I made some Kernza bread. Kernza is a grain. It's a hybrid of a relative of wheat, but it's a perennial. And so that they don't have to dig it up every fall and replant it in the spring. And so it keeps a lot of carbon down in its roots. So it's what they call climate positive. We could maybe go to grains like that. But right now it's just a boutique grain. I can't even remember which state it's grown in. And so you could.
So it's actually like a carbon sink?
Well, at least you're not turning over the earth and sending all its carbon up
Yeah, right.
every year.
So it's actually
Yeah, keeping carbon
fixing carbon
in its roots.
yeah.
Now it's a grass, so
Yeah.
it's not like it's
Right.
huge
It's
roots.
not a
But-
permanent thing.
Yeah. All right, thanks, everybody.
Thanks.
Thanks, Jonathan.
All right, so let's give another round of applause for Mark Iredell for coming out and presenting. Thank you so much. It's always been really inspiring for me and influential to have these conversations, throughout my life, to talk about what you've been learning and what so many scientists like Arrhenius have been studying for a century. And this is something that humans have understood for a long time, and it's something that we have really seen, the grand scheme of things of how it's all coming together. And so we really need to be more aware and more awake as to what's happening around us and what's happening in the world. Just like I was saying earlier, it's not just the facts, but the history that comes into it and the methods that people are using to investigate how the world is changing and how we are changing the world is very important to understand the correlations there. And hopefully, we can see some more change in our politics and in our lifestyles that will reduce emissions. Hopefully we can use less. Every product you buy has to be, the resources are harvested, which uses oil, it's manufactured, which uses oil, it's transported, which uses oil. And so, just everything we use, we just need to bring down on general consumption and this need for consumption, and we need to cut down on war, because military is really one of the biggest producers of carbon in the atmosphere. So thank you for coming out and sharing that. That was really inspiring, and thank everyone else who has come here. Once again, this is an open mic, so if anyone wants to share what they do and share what projects they're involved with, share their music, then this is the place to do it. So if you're inspired to share, then please come on up and talk to me. So this song was produced by my good friend Bert Loudis. He goes by Bloudis, which is his music production name. He is the founder of Lucid District, which is my music and arts collective that me and him, we throw events throughout DC and DMV area. This event in particular is called the Sustainable Gatherings. It's all about sustainability, it's all about presentations about environmentalism and humanitarianism. And it's promoting the Sustainable Dream Festival, which is going to be happening in April in Middleburg. So if you're interested in the Sustainable Dream Festival, definitely check out the information, which is by the front door. There's going to be a multi-day weekend event in April. We're connected with a lot of nonprofit organizations, environmentalism and activism. If you want to get involved in activism, then we're working with Extinction Rebellion, which hosts actions to raise awareness about environmentalism all the time. So once again, I encourage you guys to come on up if you have anything to say or have any music you want to share with the open mic.